average atomic mass. Now, contrary to popular opinion, there is not always one mass for a given element. We can have several different ones, actually. The atomic mass, as seen on the periodic table, is actually a weighted average. So this is not your typical average where we add everything up and divide by 3, but instead a weighted average where the amount I have matters. These different masses come from what are called isotopes. Isotopes are an atom with the same number of protons, so it's the same element, but it has a different number of neutrons, so that gives it a different mass. Whenever we're talking about atomic masses, we usually also mention this thing called percent abundance. So if you think of the Earth as one big pie chart, the percent abundance tells us how much of that element on planet Earth is a particular isotope. So you could have 15% carbon 12 and 0.001% carbon 14, or whatever the actual percentages are. And it's those percent abundances that allow us to create this weighted average when we're trying to determine the mass that would appear on a periodic table. So this first example is asking you to find the average atomic mass of oxygen given the information below. So this gives us 3 isotopes of oxygen, each with its own percent abundance and its official mass in atomic mass units, AMUs. So we have the name of the element, and then 14, this is the isotope. That's protons plus neutrons. It's the mass number. And the formula that you use whenever you're trying to find average atomic mass is we do percent abundance times the mass. But you have to remember to take the percent abundance out of percent form. Sometimes it's easy to forget. So I like to put it over 100 in my formula just as a reminder. And that times the mass that goes with that particular percent abundance plus my next percent abundance divided by 100 times its mass plus so on and so forth. So you will have as many terms as you have isotopes. This problem has 3 isotopes, so I will have 3 terms like this. Go ahead and put the third one in here. So now we're just going to fill in my numbers where they go. So I have my first percent abundance here is 0.52 divided by 100 times the mass that goes with 0.52, which is 14.003, plus my next term, 39.83 divided by 100 times its mass, 14.999, plus 59.65 divided by 100 times its mass of 6.13. Now I'm going to go ahead and do this in smaller chunks. In case you're doing this along at home, you can maybe see where your errors lie. I put these in parentheses specifically because that's how it needs to go into your calculator. You know order of operations, but your calculator does not. So you have to make sure that you are, in fact, telling your calculator the order in which you want it to do things. Like we want these 2 numbers divided, then multiply by 14.003. So my first term, I get that, plus, let's see, my next term, 39.83 divided by 100 times 14.999. 5.974117. And if you're doing it this piecemeal method, you need to make extra special sure that you're carrying out your decimal places really as far as you can stand it. Because every time you round, you introduce a little bit of error into your calculation. So let's see, I got all my numbers there. Let's add them all together. Forgive the delay while I type all of these big long numbers back in my calculator. If you have one of the monstrosities, these big old TIs, make sure you use that thing's full capabilities in being able to carry these numbers throughout. It makes life much simpler. Whoop, and I have a typo in mine. Haha. It's 5.9. There we go. Equals, when I add all those together, 15.668. We'll stop there. AMU, since we're talking about atoms. Now, before you leave me all kinds of nasty comments that say that, but on the periodic table, oxygen's mass is 15.9998. I made this problem up. This was just meant to be an example. Ideally, yes, you are correct. You would be able to double check your mass on the periodic table. They should be pretty close, but I made this one up. Sorry. So, this is the average, the weighted average, of our oxygen. Oxygen. Sometimes you will see problems that instead of asking you to calculate the average atomic mass, it asks you to find information that is missing. In this problem, I was given the average atomic mass directly off of the periodic table this time, and asked to fill in the information that is missing. I'm missing a percent, and I'm also missing a mass. The easiest place to start is this right here. We said the Earth is like one giant pie chart, which means all my percents should sum to 100. So 5.63 plus the one that I'm missing plus 9.37 should all give me 100. So by subtracting the 2% I have from 100, I find out that my missing percent is 85. So this is the missing information for my first blank. Now all I need is the mass. Since this is an average atomic mass, I'm going to use the same formula that I used before. Percent abundance divided by 100 times the mass plus however many isotopes you have equals your average mass. This time I'm going to have a variable, something I don't know. In case you haven't noticed, I like using question marks. That's just me. So let's plug in everything we know in this formula. I know my first percent abundance there, divided by 100. It has a mass. There's my first term. Plus, on my second term here, this was where I have my unknown information. I now know that my percent is 85. But I still don't know my mass. My last term, I have a percent. I also have a mass. And since this is finding average atomic mass with an unknown in there, they had to give me the average atomic mass. I can only have one variable in my equation. Wow, my writing got smaller. So, I gotta get that thing by itself. So let's start simplifying some of these parentheses. First one here, times 29.150, 1.641145, plus, let's go ahead and simplify that down. Plus 9.37 out of percent times 31.041 is 2. I don't know why I put the parentheses there, but that's okay. Equals 30.97. Now we get to actually start the algebra of getting that by itself. First, let's add these two things together. I'm taking the long root just so you can see all of the steps that I do. Plus 2. So I'm adding these two numbers together, and I get 4.549667 plus our 0.85 times my question marks equals 30.97. Almost there. Subtract this big old thing from both sides. We're still going to get that by itself. That's our whole goal through all of this algebraic nonsense. Don't tell your algebra teacher that I said that. equals 30.97 minus 4.5 stuff. 26.4203133. Whoops. Last step, I got to get rid of this 0.85. It's being multiplied on this side, means it will be divided over here. So if I divide it on both sides, top and bottom can cancel. My question mark equals 31.083. We'll stop there. So whenever we're missing information, you still use the same equation. As long as you're doing weighted average atomic mass, you're always going to use this same equation throughout. The only difference is what you're solving for. If they give you the average atomic mass, then you're going to be looking for something inside the equation itself. But it's all just algebraic gymnastics. So I hope that clears up any questions on average atomic mass. As always, if you get stumped, let me know. And happy algebraicing!